For our first talk, I would like to introduce now Professor Yutaka Ishikawa, who was the project leader of the post-K supercomputer development. From 1987 to 2001, he was a member of the National Institute of Advanced Industrial Science and Technology of the Ministry of Economy, Trade and Industry in Japan. From 1993 to 2001, he was the chief parallel and distributed system software laboratory developer at the Real World Computing Partnership. He led the development of a cluster system software called SCORE, which was used in several large PC cluster systems. From 2002 to 2014, he was professor at the University of Tokyo. He led the project to design a commodity-based supercomputer called the T2K, Open Supercomputer. 3 universities, Tsukuba, Tokyo, and Kyoto, each obtained a copy of this supercomputer in about 2008, and you can learn more of its progression at the exhibition hall downstairs. He's been involved with the design of the post-2K machine since 2013, which will be operational in 2020. So with a talk on system software and the post-K supercomputer, Professor Ishikawa.
So thank you for the introduction. So today I want to talk about our system software stack in post-K supercomputer. And so I added the subtitle. It's Revisiting Separation of Mechanism Policy in HPC. The notion of separation of mechanism policy has been widely well known in the OS community to design the new system software stack. And I think that if you graduated from the computer science department, you might learn this notion at the operating system course. So this is very well known, the notion, and I'll explain what does this mean later. And so today's talk is essentially the two items, and one is an overview of FLAGSHIP2020 Project. That's our Japanese national project will be introduced, and then I talk the design philosophy and introduction of system software stack, especially operating system. So this slide shows an overview of FLAGSHIP2020 project. And so that's the government project. And so it has 2 missions. One is, of course, to build the Japanese national flagship computer. It's currently, the code name is post-K. And so this means that this will be the successor of K computer. And the other mission is to develop a wide range of HPC applications. And so those are running on post-K in order to solve social and science issues in Japan. And so developing post-K computer, that's the RIKEN AICS is in charge. And we selected Fujitsu as a vendor partnership. And the project was already started since last year. And so we ran almost 1 year and a half. And so during those 1 year and a half, we have been designing the basic concept and designing the architectural parameters. And currently, our design have been evaluated reviewed by the reviewing committees. And after the evaluation of our basic design, then we proceed to design and implement the hardware and system software. And so then the current schedule is from 2018 to 2019. machine will be manufactured and installed and tuned. And in 2020 fiscal year, that's from April, the machine will be operated in general purpose. So this is just an overview of architecture. So because we had just ended the basic design, and now the reviewing. And so we today, so I cannot describe the detailed architecture, but you might imagine what kind of architecture would be is from the Fujitsu's latest supercomputer, that's FX100. And so the right-hand side, this is the overview of the Fujitsu latest supercomputer, FX100. And maybe so if you visit the Fujitsu booth, then so you will see the actual specification and also the hardware. And so this is based on the Spark architecture with Fujitsu's extension for HPC. And each node has 32 compute cores. And in addition to that, 2 assistant cores are integrated. So those 2 cores are for running the operating system, the activities, daemons. And the peak performance is over 1 teraflops, and 32 gigabyte HMC technology is used, and interconnect is the successor of K-Computer's interconnect. It's called TOFU2. And so the post-K will be also the manycore architecture. And for the storage system, we are now planning to provide the 3-level hierarchical storage system. That's the silicon disk, magnetic disk, and storage for archive. And so this is just a picture of the system software stacks. And we have been developing our own on lightweight kernel with Linux kernel. And on top of that, the several advanced features are integrated. And of course, we provide the MPI and the parallel the libraries, and also the several programming languages and the tools. And so then I'm going to the design, describing design philosophy. And actually, so the 3 items. So the first one is, so of course, we lesson learned from K-computer development and the operation. And during the K-computer development, the RIKEN selected several benchmark programs from the users, and then the machine was designed and evaluated using those benchmarks. And so at that time, so as long as I understand, the application developers limited the involvement. And but also in the post-K computer development, so we involve the application developers to co-design the system architecture. And also, we reviewed the K-computer, and so we found that some limitation of the post-K-computer, and we will fix those limitations. And so I introduce some of them. So one is that so of course the K-computer, we use Linux kernel, And, but unfortunately, not all languages tools available in AICS, the architecture provided, just there are few. And especially Java environment is not supported by Fujitsu. Another example is, in the MPI, the runtime system, so only a single MPI job may run on each node. And so that means, if you want to run the more than one MPI jobs within each node, but it's not allowed. And so unfortunately, this is not an operation policy, but actually the implementation limitation. So we have to fix this limitation. And the third example is that the K computer employs file staging, and but the file staging causes unnecessary file movement. So it seems the user do not specify exact required files, but they just required just specify the directory, and then the files under the directory are moving to a local file system in a staging phase. And that causes the extra file movement. So we will not use the file staging, but so provide the file I/O asynchronous facilities to get the better performance. And this is the final example. And so we review the equipment, redundancy, and the system software stack, especially for our parallel file system in terms of the RAS capabilities. And so now we design how much the equipments are required for the RAS capability, and also how to survive the node against the file systems the failure. So the third design philosophy is Codesign Trinity. So this means so not only the architecture and the application developers co-design, but also the involving system, the software and programming language developers. So three areas are corporately designing the system. Oops. So this slide showed the overview of our co-design. And so Japanese government has selected 9 social and scientific priority issues. And also they selected the R&D organization. Okay. That's for the high priority issues from the social and national viewpoint, and also the promising creation of world-leading achievement and promising strategic use of post-K computer. And here's a target application. And so we discussed with those 9 organizations to select the target applications. So each organization gave us the one target application. So in total, we have 9 target applications. And so those are listed here. And it's related life science, preventing the disaster, weather and climate, and the basic science, and industrial applications, and the energy issues. And with using those target applications, so the left-hand side is listed the co-design element. And in terms of the node and storage architecture, so those parameters are defined. And so during the basic design phase that already ended, And we almost decide the similes length and the number of cores and the Newman nodes and those properties. And in terms of system software and programming environment design, so we especially focus on operating system, communication libraries, and file IOs. And so we are now thinking of again using the raster-based file system. Actually, the K-computer, the Fujitsu enhanced raster file system has been used. And so we continue to use that file system. That's current our design. And also the math library and domain-specific libraries have been the design. So, sorry. Sorry. So let me explain the Codesign elements in systems software. And so we are now finding out what kind of the capabilities are needed by application. And also application developers will understand the capabilities provided our system software to get the well-suitable runtime environment for their purpose. And so in collaboration with applications, so here's the Codesign items. And so let me explain a little bit about those items. And so if the number of threads of an application is exactly the same the number of cores, so this means no CPU scheduler is needed. So what does this mean is so we remove the hardware timer interrupt, and actually timer interrupt, hardware interrupt is one of the big source of OS noises. And so if the user do not need a CPU scheduler, then the operating system staff doesn't use the hardware interrupt timer. Then so we eliminate the OS noise. And so most HPC applications do not need actually demand paging. So demand paging is actually the base mechanism in the general purpose operating system. But so the most application, HPC application actually do not need that. Instead of that, the physical memory is eagerly allocated to the user space so that no page faults happen. Okay. And the third item is supporting efficient consecutive job execution. So that means so one of the application is a kind of real-time application, and it's periodically running and needs the real-timeness. And so this application is actually so real-time local weather prediction using observatory big data. So I will explain this application later in this talk. The Codesign with node architecture is the items are two. And so in case of the each process assigned in each NUMA domain, then the physical memory area, including OS working memory, should be allocated with respect to process location. And so we want to implement such kind of capabilities in our lightweight kernel. And also the application needs efficient intra-node MPI execution environment for strong scalability. And so we should think of the good mechanism for intra-node communication. And so others also the several design items, but so due to the time limitation, I'll skip the explanations. So how system software should be designed. So this is the issue. And so going to the third design philosophy, the separation of mechanism and policy. So this is very the old notion. And back to 1970, in Brinch Hansen's paper, he stated at that time the several operating systems just providing a single mode of operation, so such as batch processing, priority scheduling, real-time scheduling, or conversational access. And he addresses the operating system should not define functions that satisfy specific operating needs, but rather to provide a system nucleus for the extended the capabilities. Okay. And after that, in 1974, the Wolf, from the Carnegie Mellon University, uses the separation of mechanism policy, the notion, and so that's the basic design philosophy for Hydra operating system. And Hydra operating system is the use on the C.MPP in Carnegie Mellon University. Okay. So let me explain again what separation of mechanism and policy is doing. And so OS developer provides the mechanism, not the policy. And then the system designer or administrator will decide the policy using a mechanism. And so this is a traditional separation of mechanism in general purpose operating system. And but even the developer believes that enough mechanisms are provided. But in HPC environment, some policies were actually wired to OS from HPC user perspective. And so application need their application-specific features to get benefit from the machine capabilities. So let me explain the examples of such kinds of mismatching or the conflicting. And so in general purpose the kernel, so in memory management, so as I already told you, but so demand paging is very popular, and that's the mechanism, and to define replacement policies. So OS developers believes the demand paging is mechanism. But the replacement, the algorithm are policies. So that's why they provide the demand paging with the selective, the replacement policies. But so again, so I already told you, so actually HPC, the applications, so some applications might need the demand paging, but the most applications do not need the demand paging, but so memory, physical memory should be eagerly allocated. That's much faster than demand paging. And in terms of the process and thread, so usually so the notion of process thread and its operations are defined in operating system, general purpose kernel. So we think the some application-specific process thread management is needed, and so we have to. it is needed to replace these mechanisms. And the process scheduling, so that's also I already mentioned, so I'll skip this one. Okay. And so we think, so there are the several mechanisms that will be conflict by user to user. And so we think we should provide the mechanism for some users, and then they provide another mechanism for another user. And some mechanisms might be a conflict, and so we can't integrate those mechanisms. So, so this picture shows we are designing and developing a lightweight kernel. It's adaptable. And so OS developer will provide the mechanism for users. And some different mechanisms will be provided for the different users. And then the user or system designer or the administrator select the policy. So unlike the general purpose operating system, so user also can be involved with the selecting the policy. That's the big requirement, as long as I understand. And so here's our McKernel approach. And so this is our lightweight kernel. It's called McKernel. And so in McKernel is running with the Linux kernel. And so resources are partitioned, one for Linux and the other for our lightweight kernel, McKernel. And so so Linux side, it's a full Linux kernel. It's running on some cores, and it's actually partitioned. And the system daemons, and if the user want to run the institute non-HPC application, then such kind of application also run on the Linux kernel. And also the device drivers are integrated to the full Linux kernel, not our lightweight kernel side. And so our lightweight kernel is only on that kernel, the HPC application running. And so McKernel is the loadable module from the view of the Linux kernel. And so currently, so McKernel runs on Intel Xeon and Xeon Phi, and also the Fujitsu FX10. And eventually, of course, this McKernel is running on our post-K machine. And also the McKernel provides the almost full Linux API, including not only the system call, but also the file system, special file system, /sys or /proc. And the lightweight kernel only provides the limited the system call, such like the memory map, process, thread management, and the signaling stuff. And the rest of the full Linux the APIs are delegated to Linux side via McKernel. And then after the processing the Linux APIs the function, then the results are going back to the application by the lightweight kernel. And so this is the open source, and you can also get our McKernel. So this slide shows how we use this environment. So again, so Linux kernel and we have the Linux kernel and the loadable lightweight kernel, McKernel, and we assumed Linux kernel is resident, and the daemons for job scheduler and several the applications needed the full Linux environment is running on that kernel. And the MC kernel is dynamically reloaded. In some sense, it's rebooted. And so if application does not need the scheduler for strong scalability, and also because application just uses the exact the number of cores, then it doesn't need a scheduler. Then MC kernel without the scheduler is the loaded and then run with the application. And after finishing the application, then going back to the initial state, just the Linux kernel running. And another job is launched. Then the lightweight kernel is loaded and run. And so in this example, so application requires the scheduler. That's because over the number of cores, threads are running. So then it's required. And so such kind of application, of course, the lightweight kernel with scheduler must be invoked. And also, if the user want to use full Linux the capabilities, then run the full Linux on the node and use the Linux the features. Okay. So this slide showed how the OS noises eliminated in our lightweight kernel. And left-hand side is the Linux with ISO's CPUs. And the right-hand side is MC kernel's results. So we took the FWQ, that's distributed by Lawrence Livermore. And so this benchmark measures how the execution is jittering. And so x-axis is the time scale, and then the y-axis is actually how much the execution time is required. And in MC kernel, it's flat. So that means almost no OS noises happen. But the left-hand side, so you see the several diversions. And so this means the several OS noises happening. And OS noises, if there are so many OS noises, then the strong capability is degraded. And so in that case, the application should run using the MC kernel. So this slide showed the Codesign example. And so we currently, we have been looking at the two big data applications. And one is this research project. And this is the weather, real-time the weather prediction. And so in this research, 30-second responsibility is required. And so every 30 seconds, the new observable data are coming from the phase array, weather radar. And also every 205 minutes, the observable data from satellites come. And so getting those the data, and then the results of the simulation is assimilated with the observed data. And so every 30 seconds, the data simulation must be performed, and then after that, another 30-second weather prediction simulation must be performed. And also, it's the ensemble simulation. And their requirement is the 100 case the ensemble simulations. And one of the ensemble simulations will be taken and to predict the 1 hour or 30 minutes weather simulation. So those are also the within 30 seconds. So this kind of the hard real-timeness might be realized using a post-K computer. And so the downside, it's related to genome processing. It's so they use several the open source code, and so many the files are the transferred between the tools. And so this is just some of the workflow in this genome processing. Oh, sorry. And so to meet this real-timeness, actually, currently the data simulation and the simulation, the data transfer is done via file system. But to guarantee the 30-second real-timeness, we have to reduce the data transfer. So instead of using the file system, data should be transferred to the another the side. And so this is the one design criteria. And this slide shows the how the file system should be designed. And so this table shows actually in terms of the file liveness, we can specify the file liveness using two matrices. And local, whether the file is in a local in each compute node or shared by compute node, and also whether or not the file is living within a single job or across job. Okay. In the most files, most files in genome processing are temporal and in the local. And so in that case, actually, if they are and also the files are very small size, and then maybe the data can be inside in memory, not need to move to the first storage layer. And in case of the real-time weather focusing, then the data is exchanged between two jobs. And in that case, without the data storing the data to file system, data should be transferred to the another job directly using the RDMA engine. So this kind of the design we have been doing. So now going to the conclusion. And so I have been presenting how the separation of mechanism policy is important in HPC. And so actually, mechanisms are defined based on application demands, not system designer and administrator. And OS kernel must be extendable for future application demands. I mean, design a new mechanism. And also, policies must be determined by application, not the administrators nor the higher level system designers. And so, Codesign results in separation mechanism policy, and that means Codesign doesn't mean defining policies by the OS designer. Rather, the designing mechanism, what kind of policies needed by application, developers or user, can be implemented. So that's the perspective from the OS designer. Okay. And so we continue to co-design a system software stack. And so this is almost the final remarks. So RIKEN would like to contribute our open source stack to OpenHPC community. And so MC kernel version 1.0 is released now. And so it's distributed from PC Cluster Consortium. And the booth number is 318. And so please visit us. And also, so we have the several the open discussion scheduled and also the tutorials are scheduled. So if you are interested in our MC kernel, so please visit us. And also, my colleague will present this noon's BOF. The title is Operating System and Runtime for Exascale. So if you are interested in the OS for Exascale, please attend this BOF. So this is the final remarks, but not least. And so RIKEN booth is 2521. And at that booth, so several outcomes are shown. So if you are interested in the current the K computers the outcome, so please stop at this booth. And also our post-K project also shown in this booth. So thank you for your attention.
Thank you, Professor Ishikawa, for articulating what's often perceived as a conflict between separation of concerns and co-design. And we have, I guess, time for one question. Of course, you can have an open session at their exhibition booth. So I'd like to commend both speakers for having the courage to follow a presentation from a Hollywood actor with technical presentations. And I would like to call our second morning speaker to the podium, Dr. Ali Dogru, to set up here. Thank you again, Professor Ishikawa.